Welcome to the course of multi-agent learning. Today we're going to discuss Bayesian play. Bayesian play in some sense can be considered as the nec plus ultra of multi-agent learning because you actually hypothesize a number of possible learning strategies of the opponent, and then by maintaining a probability distributions over the conceived or hypothesized learning strategies of the opponent, you actually try to predict which of those, reply rules of the opponent is plausible. In order to understand, so Bayesian play is by far the most sophisticated learning algorithm, which theoretically is very interesting, and it can be implemented also, but you have to simplify matters a bit. So you need to know what Bayes' rules is, have some knowledge of elementary probability theory. Then I will give some examples of Bayesian play. I will give a demo with NetLogo of Bayesian play. Then we will discuss the formalism. Bayesian play can be molded into Jordan's framework, which is to split it into a reply rule and a forecasting rule. So a forecasting rule tries to predict the mixed strategies of the opponent in the next round, and your reply rule specifies your mixed strategy in the next round based on the history, and together those two give a predictive learning rule. I will discuss predictive learning rules in the context of Bayesian play, and an interesting result of Kuhn in order to simplify predictive learning rules. We'll talk about the true distribution of play, so the play as it will actually unfold in the course of time, versus a subjective distribution of play, that is, the play as either one of the players sees it as it unfolds in time. For the main results we need the concept of a domination of measures, also known as absolute continuity, and we can formulate two results of Blackwell's and Dubin's about being a good predictor of the distribution of play and a very good predictor on the distribution of play. On the other hand, we have a notion of absolute closeness of two probability measures. Two probability measures can be absolute close, and then there is the theorem of Kallai and Lehrer that in a rough sense says that if a player gives all potential play paths a small positive probability, so that means that the true distribution of play must be given a positive probability at the outset, and that is called by Kallai and Lehrer a grain of truth. And if that is the case, then eventually the subjective beliefs will be absolutely close to the actual realization of plays. Okay. So the results are from the publication of Kallai and Lehrer, and Peyton Young draws upon, in his chapter on Bayesian learning, draws upon the results of Kallai and Lehrer very strongly. Shoam has a small exposition on rational learning in chapter 7, section 3. Although it's very short, and so it merely enumerates the results and does not go very deep into the theory. So it's not really good self-contained discussion of Bayesian play. And there is an interesting article with practical applications of Zheng and Katja Sikara on Bayesian learning in negotiation, but we don't discuss that. I just want to mention it here as an example of a practical application. So first we will discuss some elementary probability and Bayes' theorem. So first, in order to understand Bayes' theorem, we need to understand the concept of conditional probability. If you have an event f of which the probability is non-zero, then you can talk about the conditional probability given that event f as, or you can write it down as the probability that event E will take place given that event f takes place. So what's the probability that a dice will show a 3 if given that the number of eyes is odd? Then that's one third, because the probability that you will throw a 3 and that 3 is odd, well, that 3 is automatically odd number, is 1/6, and the probability that you will throw an odd number is a half. So 1/6 divided by 1/2 is 1/3, and that's exactly the probability that you will throw a 3 given that you will have thrown an odd number. It can be shown that conditional probability is a probability measure on itself, in and of itself. And if Bayes' rule says that if you don't know the probability of E given f, then sometimes you can reverse the conditional probability like so, and you have to multiply it by the probability of E and divide it by the probability of f. Bayes' rule immediately follows out of the definition of conditional probability. You can prove it just by rewriting conditional probability, because the probability of f given E can be also written as probability EF divided by probability E. And if you write that, then you can distill Bayes' rule. If you talk about this probability here, then you can talk about the probability of, if you talk about this probability here, you can talk about the probability of E given f. Then you know that f already happened, and that's called posterior probability. If you didn't know that f already happened, then you talk about prior probability. So you should really do this exercise with arbitrary numbers. If E is influenza and F is fever, then often it is known what the probability of having fever is given that you have influenza. But in practical and you know what so if you want to compute the probability that you have influenza given that you have fever, you compute the probability of fever giving influenza and then dividing by the probability of having influenza multiplying by the probability of having fever. Often you don't know these two either, but you can marginalize them like so, and then you can often compute the probability of having influenza given that you have a fever, because you know this probability, which is this probability here. The prior probability of influenza is also known, and its complement is known. And probably what also is known, the third data you should have, is that the probability of having fever when you do not have influenza. So in order to compute the left hand side, you must know three quantities. This one, probability of F given E, the probability of E, and the probability of F given not E. And then you can compute the reversed conditional probability. So that's Bayes' rule in a nutshell. If you want to know more about this, then you may consult, for example, Sheldon Ross' Introduction to Probability. So for continuous random variables, this works the same way, only you don't sum over all the marginal events, but you have to integrate over all the marginal events. So for Bayes' lemma, this means if you want to know the marginal density, now you want to know the density of x given a certain value of random variable out y, then by definition that's the joint density of fxy divided by the density of y. And by definition, that is the posterior density of y given x times the density of x divided by the density of y. And you can marginalize this 1 over all values of x, like so. So just to show that these that the Bayes' theorem for continuous random variables is expressed in terms of density functions. So this function is called the joint density, and this function is called the prior density, posterior density. And then we talk about the marginal densities. So with Bayes' rule, it is possible to compute. So this is probably one of the most important slides of the presentation. Given Bayes' rule, it is possible to compute the probability that an opponent has a certain reply rule given the history of play, and that for every player. So at the outset, you will have to have a possible arsenal of reply rules of the opponent ready. We assume here that we have only one opponent, but the discussion easily generalizes to multiple opponents. So at the outset, you have to have a set of possible reply rules of the opponent. This may be an infinite set, a countable infinite set, or an uncountable infinite set. But you have to have those ready at the outset. Now, of course, the opponent maintains an actual reply rule, which you don't know, but you hypothesize that this might be one of these. Now, at the outset, you give every reply rule a prior probability, like so. And often it is convenient to give every reply rule the same probability. So you divide the probability uniformly over all reply rules. And of course, the question you are interested in is the probability of the case that the actual reply rule is equal to GI given the history, because the history reveals information about a possible reply rule. Now you can't compute, of course, this probability right away, but you can compute this probability here. The probability that you will observe a certain history if you know that the opponent uses a reply rule GI, you can of course compute. I will show you in a moment that it is indeed very easy for certain reply rules. Times the probability, the prior probability that you have given that the opponent's actual reply rule is the hypothesis reply rule G sub I, divided by the probability of the history itself. Now this one cannot be computed right away either, so you have to marginalize it over all possible strategies. So if the probability of the history is marginalized over all strategies, you will obtain this one. So if you don't understand what marginalization is, then consult, wait, I have to look it up. Well, you can consult Introduction to Probability of Sheldon-Ross, or or you can consult this one. Interesting links, covers of books. So this is one book I can recommend, First Course on Probability of Sheldon-Ross. And also this one, A Modern Introduction to Probability and Statistics of Dekking, Krijkamp, Lopuhan and Meester. So basically you divide up the probability of the history into, well, you conditionalize them by the possibilities of having present one of those hypothesized reply rules of the opponent. And then we obtain this rule, which is to say the probability that you indeed have his reply rule G sub I can be computed like so. Well, this one is easily computable. This one is the prior probability of G sub I, as well as this one. And, well, this is just a summation of all the other alternatives. In order to this is basically a term to normalize, so that you have a probability on the left-hand side. So, in the case if you have chosen identical priors, like so, and effectively the probability of that you are interested in is just the reversed conditional probability, or is proportional to, this is the sign for proportional to the reversed conditional probability. Of course these numbers don't add up to 1, therefore I say proportional to. But if you normalize them like so, then they will add up to 1. So basically you compute the probabilities on the right hand side, normalize them, and you have those probabilities here. So that's the essence of Bayesian play. So in order to understand what's going on, I will give a demo and then some examples. So in the demo I will hypothesize among reactively reply rules in the setting where we have two players and those two players play two possible actions, cooperate and defect. The payoff matrix in this case is not interesting, but their behavior is, so cooperate and defect. So a possible strategy of your opponent is, for example, always cooperate, or unforgiving. Unforgiving means cooperate until the opponent defects, and then you will defect forever. So your opponent may play unforgiving. He may cooperate 90% of the time. He may play tit for tat. So your opponent may just mimic your moves. Your opponent may play just 10%, which is to play tit for tat 90% of the time and defect 10%, the other 10% of the time. Your opponent may the non-deterministic strategy majority, which is to respond with the action that you most played. So if you played cooperate 60% of the time and defected 40% of the time, your opponent typically will play cooperate because you have played cooperate most of the time. And equally, so the majority is deterministic, and equally is the non-deterministic variant of majority. That is, if the opponent played 60% of the time cooperate and 40% of the time defect, then equally plays with 60% probability cooperate. So for example, the G1 to G sub n may be consist of those reply rules here. And then we'll give so this is the demo, and the example will discuss how to learn reply rules in the repeated prisoner's dilemma or in the coordination game. So we'll now give the demo. Here. So, well, that's nice. So you see here all hypothesized strategies here, all cooperate, all defect. Flip a coin, which means, well, you can see it here, flip a coin, that is just randomly play cooperate or defect, half and half. This is play randomly cooperate and defect by playing cooperate 10% of the time, play cooperate 90% of the time. This is unforgiving, tit for tat, Pavlov. Pavlov means cooperate if and only if both parties played identical in the previous round. So this Pavlov turns out to be a strong learning strategy. Therefore it's incorporated. A majority and easily sound just very plausible. And JOS is a plausible learning strategy because tit for tat is quite a strong learning strategy. And sometimes you can sneak out by defecting some of the time. So each reply rule has a color, and the probability of either one of those reply rules is 1. You see here the probability of those is 1 because there is no strategy of play. And if there is no strategy of play, the probability of the history given the strategy, the probability of having the empty history given that reply rule. So I should change this into reply. So I've now changed strategy into reply. So probability of the history given the reply rule, that's easy to compute, and this one is possible to compute given Bayes rule. So double R stands for reply rule, and this is Bayes formula. So at the outset the probability of every history is 1. Then we just let row cooperate 70% of the time and let col cooperate 70% of the time, and row's task is to predict the reply rule, or to give probabilities to the reply rules of the opponent of col given the history. So if they both do one step, both have cooperated in the first round, then you see that the column of defect all is has vanished, because the probability that we have, the probability of history that both cooperate, giving that the opponent serves itself of the all defect reply rule, is 0. So we can now be sure that the defect that the opponent doesn't play defect all. And the probability that the opponent plays cooperate 10% of the time is the probability of the history times the probability that the opponent played cooperate in the first round. And the probability that an opponent that serves itself of the C10 strategy plays cooperate in the next round is exactly 1/10. And the probability that the opponent plays cooperate if the opponent serves itself from the C90 strategy is 90%. All the other reply rules are given 100%. All the other histories are given 100% probability given the reply rule, but because for all the other reply rules, play cooperate in the first round. All cooperate plays cooperate in the first round. Unforgiving plays cooperate in the first round. Tit for tat plays cooperate in the first round. So the behavior in the first round coincides with what those reply rules prescribe. Majority plays cooperate in the first round, and so on. So let's move on to the second round. I don't know what those, or we don't know what the parties will play in the second round. There's a 70% probability that they will play cooperate. So let's, again, they will cooperate. So the probability that C10 will cooperate twice is 1/10 times 1/10 is 100th. And the same with C90. The probability that C90 will cooperate 2 times in a row is 0.9 times 0.9. And for all the other reply rules, 2 times cooperating in a row, if first player cooperates, is still in line with unforgiving, still in line with tit for tat, still in line with Pavlov, and so on. You see the probabilities quickly decrease because either of the histories is rare. So those probabilities in the first plot will quickly decrease, and here the same probabilities but normalized, they will receive moderate values, so you can still read them off from the plot. So let's play a third round. Step. Now the first player defects and the second player cooperates. This is still in line with unforgiving, tit for tat, Pavlov, majority and eitherly. And for 0.81% in line with just. Just is a bit hard to explain, so we'll devote a separate slide to it to explain how this probability is computed. So, but these are easy to see. Well, let's play a fourth round. Now, because tit for tat should echo the first player, it should play defect. And since the opponent doesn't play defect in the fourth round, because it played cooperate, tit for tat, which is the purple one, is completely eliminated as a possible strategy. So it's probability of this history here, given tit for tat, drops from 1 to 0. So it's completely eliminated. As for Pavlov, as for what are the other two? Unforgiving, because unforgiving should have played defect as well. Unforgiving says play defect as soon as the opponent plays defect, and defect ever after. So the probability of unforgiving suddenly drops to 0 as well. And Pavlov as well. So, and the probability of all cooperate, that the opponent plays all cooperate, is still 1, because the opponent has played cooperate all of the time. And majority is still 1, because the proponent played 3 times over 4 cooperate. So indeed, the opponent should play cooperate all of the time. So this history is completely in line with this possible reply rule, which is majority. Now you see that here the probabilities in the first plot very quickly drop to 0 or go to 0, while the normalized probabilities indicate the probabilities of the reply rules given the history through Bayesian formula, which must always add up to 1. So these plots give information, and this plot gives information. The first plot gives little information, because very rarely all probabilities drop to 0. Oops, sorry. Let's take another step and another step. You see, eitherly becomes less plausible, because eitherly plays cooperate defect in the same proportion as the first player, but this cooperate here in the 6th round, well, this should for majority it doesn't hold anymore. Oh yes, it does, because it's 1 over 1. 3 cooperate and 3 defect. And for eitherly, this history here is the probability that you will play cooperate in the 6th round is 50%. So you must multiply eitherly with 0.5 here. Let's play another round. You see, majority, the probability that this history will show given that the reply rule is majority is 1, because this is still in line with the history. Let's proceed, round 8. Now here should the majority strategy cooperate, because the majority of the actions are cooperate. You see, 1, 2, 3, 4 cooperate, and only 1, 2, 3 defect. So majority should have played cooperate here. It doesn't, so we can completely rule out this history based on majority. Note the bars have now different colors. The lucid colors display the probability of the histories given the reply rule, so the first plot, and the dark bars display the probability of the reply rules given the history. And now the probability that you deal with eitherly given the history is quite high. It's almost 1. So let's proceed. You see, the probability of the histories of this history here, given flip a coin, cooperate 10%, cooperate 90%, is still non-zero, because it's still possible. It's very unlikely, or it's quite unlikely, but it's still possible. The other reply rules are ruled out. Now, if we normalize the probabilities of the histories, we obtain the probability of the reply rules. And we see that given the history of play, it is highly probable, you see here, that we're dealing with eitherly. Actually, we're dealing with play 70% of the time, cooperate. So this is the actual, this one is the actual strategy of the column player. We know. But Bayesian play thinks or deems it most plausible that it's dealing with eitherly, because this is the given arsenal of strategies it got. So these are the, what is it, 1, 2, 3, well, these are the 10 strategies, the 10 reply rules it has to work with. And of those 10 reply rules, it deems eitherly most plausible. You see that the probability of the histories all go to 0, because the probability of history itself is very rare. It's very rare that exactly this history is played, of course. But if you normalize those probabilities, then eitherly will emerge as a winner in the long term. Well, let's do a few more. You see it will approach 1. Okay. Now let's do it again, and let's put the second player on a strategy, on a reply rule that is in our arsenal of hypothesized strategies. Hypothesized reply rules. Yeah, some authors name reply rule also strategies, like for example Peyton Young. So therefore I completely interchange reply rule and strategy, but reply rule is better. So if Bayesian learning if it should function at all, it should converge towards C90. C19 is has color lime, light green. So it should converge to this strategy. So let's see what happens. So because we're now in the 7th round, and up until now both parties have cooperated. So it is very likely that the column player is an all cooperate player. But it's also very likely, well, consider the histories, that the opponent is either unforgiving, tit for tat, Pavlov majority, or eitherly. As soon as the opponent starts to defect, which is 10% of the time, all those are ruled out, as us all see. So as soon as the defect will emerge in the second column, then those positive strategies of all cooperating will be ruled out. So let's see. Well, row player defects, but that doesn't have an effect on the estimated reply rules of the opponent. So let's continue and let's wait until the until the opponent defects. Now you see that, well, eitherly is still very plausible because the history still concurs very much with eitherly. Eitherly plays cooperate defect as a reflection of the frequency, the empirical frequency of the row player, and it's very much in line with eitherly. This reply defect is very much in line with eitherly. So let's proceed. Well, in the long run, the history of play is no longer a proper reflection of eitherly anymore, and indeed Bayesian learning will recognize now that the column player indeed plays 90% cooperate all the time. And you will see accordingly that the probability that we're dealing with C19 is converging to 1. So you see, Bayesian learning is very intelligent learning strategy. Still, this is partly half of multi-agent learning, because Bayesian learning is able to find out which reply rule the opponent is using here in this particular example. But we still, if we have to have a complete multi-agent learning algorithm, we still have to formulate a reply of ourselves. So if we do know that the opponent is using cooperate 90% of the time, we have to still sort out what is the best reply for ourselves once we know that the opponent is using this reply rule. So, for example, I think that's best now for us to cooperate all of the time, if we're playing prisoner dilemma, for example. But it's not important here because there are no payoff matrices. We are only concerned with predicting the behavior of the opponent. So I will stop here to make the length of the video not too long, and hope to see you on the other side. See you.